There we go. We're now live on the recording. And so we'll start out with this little video. I just went to YouTube and searched on water hammer, and I found this one about the right length. And this guy does a pretty good job. He even writes a partial differential equation in here, which I know you guys will just love to see. Here, let me get my microphone down here and I'll get this thing started.
You might know that most liquids are incompressible, or at least barely compressible, which means no matter how much pressure you apply, their volume doesn't change. This can be really useful, like in hydraulic cylinders, but that lack of springiness can also lead to catastrophic failure of pipe systems. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about hydraulic transients, also known as water hammer. This video is sponsored in part by Blue Apron. More on that later. It's easy to forget how heavy water is, since we hardly ever carry more than a few ounces at a time. But if you add up all the water in the pipelines of your city, or even just pipes in your house, it makes up quite a bit of mass. And when all that water is moving through a pipe, it has quite a bit of momentum. If you suddenly stop that movement, for example, by quickly closing a valve, all that momentum has nowhere to go. Since water isn't compressible or springy, it can't soften the blow. You might as well be slamming concrete into the back of the valve and the walls of your pipe. Instead of being absorbed, that sudden change in momentum creates a spike in pressure that travels as a shock wave through the pipe. Sometimes you'll even hear this shock wave as banging in your walls when you close a faucet or run the washing machine. Hence the superhero-esque nickname, water hammer. Banging pipes inside your walls can sound a bit spooky, but for large diameter pipelines that can be hundreds of kilometers long, that surge in pressure from a change in momentum can cause major damage. Let's do a quick calculation. If you have a pipeline carrying water that is 1 meter in diameter and runs for 100 kilometers, a fairly average sized pipeline, the mass of water in the pipe is about 80 million kilograms. That's a lot of kilograms. In fact, it's the equivalent of about 10 freight trains. Imagine you're an operator at the end of this pipeline in charge of closing a valve. If you close it quickly, you've essentially slammed those trains into a brick wall, and the pressure spike that results from such a sudden change in momentum can rupture the pipe or cause serious damage to other parts of the system. There's actually another term for when a large spike in pressure ruptures a sealed container, a bomb, and water hammer can be equally as dangerous. So how do engineers design pipe systems to avoid this condition? Let's build a model pipeline and find out. Here's my setup. I've got about 100 feet or 30 meters of PVC pipe connected to the water on one end and a valve on the other. I also have an analog and digital gauge so we can see how the pressure changes, and a clear section of pipe in case anything exciting happens in there. I mean civil engineering exciting, not like actual exciting. Watch what happens when I close this valve. It doesn't look like much from the outside, but look at the data from the pressure gauge. The pressure spikes to over 2,000 kilopascals, or about 300 psi. That's 5 times the static water pressure. It's not enough to break the pipe, but way more than enough to break this pressure gauge. You can see why designing a pipeline or pipe network can be a little more complicated than it seems. These spikes in pressure can travel through a system in complicated ways. But we can use this simple demonstration to show a few ways that engineers mitigate the potential damage from water hammer. This is the equation for the pressure profile of a water hammer pulse. We're not going to do any calculus here, but the terms of this equation show the parameters that can be adjusted to dial back these damaging forces. And the first one is obvious. It's the speed at which the fluid is moving through the pipe. Reducing this is one of the simplest ways to reduce the effect of water hammer. Velocity is a function of the flow rate and the size of the pipe. If you're designing a pipeline, the flow rate might be fixed so you can increase the size of your pipe to reduce the velocity. A smaller pipe may be less expensive, but the flow velocity will be higher, which may cause issues with water hammer. In this case, my pipe size is fixed but I can reduce the flow rate to limit the velocity. Each time I reduce the velocity and close the valve, the resulting spike in pressure decreases. Next, you can increase the time over which the change in momentum occurs. One common example of this is adding flywheels to pumps so they spin down more slowly rather than stopping suddenly. Another example is just to close valves more slowly. If I gently shut the valve rather than allowing it to snap shut, the pressure changes are more subtle. On large pipelines, engineers not only design the components, but develop the requirements for operation of the equipment. This will almost always include rules for how quickly valves can be opened or closed to avoid issues with water hammer. The final parameter we can adjust is the speed of sound through the fluid, also known as wave celerity. This describes how quickly a pressure wave can propagate through the pipe. The wave celerity is an indirect measure of the elasticity of the system, and it can depend on compressibility of the fluid, the material of the pipe, and whether or not it's buried in the ground. In a very rigid system, pressure waves can reflect easily without much attenuation. I've got flexible PVC pipes sitting on the ground free to move, which is already helping reduce the magnitude of the water hammer. I can increase the flexibility even more by adding an anti-surge device. This has an air bladder that can absorb some of the shock and reduce the pressure spike even further. Anti-surge devices are very common in pipe systems, and they can be as simple as spring-loaded valves that open up if the pressure gets too high. In water distribution systems for urban areas, water towers help with surge control by allowing the free surface to move up and down, absorbing sudden changes in pressure. Plumbing is one of the under-acknowledged innovations that has made our modern society possible. But when you harness the power of water by putting it in pipes, it's easy to forget about that power altogether. Water can be as hard as concrete when confined, and if you bang two hard things together, eventually something's going to break. If you're an engineer, your job is to make sure it's not the expensive infrastructure you design. Part of that means being able to predict surges in pressure due to water hammer and design systems that can mitigate any potential damage that might result. Thank you for watching, and let me know what you think.
So what do you think? That's pretty awesome, isn't it? Yeah, we've all probably experienced it, but you don't realize how potentially damaging. I mean, in a power plant, for example, you've got all that cooling water flow and stuff like that. You start slamming valves around, I mean, you can wreck stuff pretty quick, especially pressure gauges and that sort of thing. So anyway, I've come across some of this stuff, and then you get an idea, and I say, well, maybe I could find a video on. YouTube is amazing. Some of the good stuff they have on there. Okay, so we'll move on here. I don't know if we'll watch, if I'll record. I'll probably record all of it. And, I might ask a few general questions, like the water hammer thing. I could ask, how can you mitigate water hammer? List, which of the following is not a solution to water hammer, or pick the one that's a solution to water hammer, or true, false, or something, whatever. But this one will be a little more detailed, I think. So let's see, let's get it started.
Coming to you from virtual MIT scattered across Massachusetts. I'm Robert Stoner, the Deputy Director of MITI for Science and Technology, and I'll be your moderator today. Our intention in presenting these webinars is to cover a range of topics drawn from ongoing work in all of MITI's low carbon energy centers, and a few drawn intentionally from outside them. We want you to know what we're up to at MIT and what we think is especially interesting and important as we work toward a globally decarbonized energy system. And because we want to engage and hear from you, we're presenting live.
Well,
and we'll reserve time at the end of the session for your questions.
Hold on.
You can pose your questions anytime in the Zoom webinar format. Just type your question after clicking Q&A at the bottom of the screen, and you'll see it. We understand that not everyone will be able to view us live, and so as usual, we'll be recording this webinar so that it can be viewed offline and shared with colleagues. Please feel free to share it. Our subject today is carbon capture. It's hard to overstate just how important carbon capture is to a low carbon future, almost any low carbon future that one can imagine. Whether we're talking about capturing carbon emissions from the flue gases of coal or natural gas fired power plants, or from power plants fueled with biomass, or the tailpipes of cars and trucks, or from the air. We need technologies that can be deployed in a wide variety of situations at low cost and massive scale that capture CO2. We may put that CO2 into the ground, convert it into new materials, or transform it into fuels to be recycled over and over again through the atmosphere. Whatever the pathway, effective means of capturing carbon are the indispensable tool. Our speaker today is Alan Hatton, the Ralph Lando Professor of Chemical Engineering at MIT and the long-serving director of the David H. Koch School of Chemical Engineering Practice. Alan is also the co-director of the Low Carbon Energy Center for Carbon Capture, Utilization, and Sequestration, three big and incredibly important topics that engage the talents of dozens of our faculty, researchers, and students. Alan, we're glad to have you at the helm. And speaking of the helm is yours.
Good. Thanks very much for the generous introduction, Rob, and I'm very pleased here to discuss with you the work that we have been doing in carbon capture. Let me share my screen with you, and we can go ahead. What I'd like to do today is talk to you a little bit about some of the work that we've been doing in the area of carbon capture and some of the new techniques and technologies that we have been developing. So I don't think it's any surprise to you that carbon capture is a really important consideration nowadays because the CO2 emissions and the global temperature changes associated with the CO2 emissions have led to dramatic increases in temperatures over the globe over the last 50 years or so. What we have is a very strong correlation between the actual temperature rises. It's the temperature anomaly since about 1880 has gone up by around over 2 degrees Celsius, about 2 degrees Celsius at this point. And this is directly correlated with the amount of CO2 that has been emitted over this period and has been accumulating in the atmosphere. So clearly there's a very strong correlation here. Something was predicted by Arrhenius around 120, 130 years ago. And it is still part of our models right now. So the problem we have is CO2 emissions from fossil fuels are a major contributor to the overall CO2 budget in the atmosphere. And indeed, if we look at the United States energy emissions, the energy-related CO2 emissions from fossil fuels is on the order of about 5 to 6 gigatons per year. A significant amount of CO2 that's been going up into the atmosphere is because of coal, natural gas, and petroleum type products. If you look at the overall emissions by sector, the electricity sector is certainly a significant fraction, but so is the industrial sector, and transportation provides a huge amount of CO2 that's emitted to the atmosphere. Globally, there's on the order of about 35 to 40 gigatons a year of CO2 that's been emitted. And these, of course, are all accumulated in the atmosphere to a large extent. And it's pretty important that we try and think about ways in which we can mitigate that. The IPCC has, and others have shown that the CO2 emissions as a function of time will continue as we go as business as usual. The CO2 emissions will continue to increase with time over here. And this could lead by the end turn of the century a temperature rise of about 4 degrees Celsius, which is really unsustainable for human activities and for life on the planet. So there's a lot of interest in terms of how we can abate what kind of abatement technologies, how can we mitigate these CO2 emissions to give us an opportunity to keep the temperature rise to below 1.5 degrees Celsius. And what this means is that the CO2 emissions should be dramatically reduced over the period over the next 80 years or so. And indeed, at some point, around about 2050 to 2070, we're going to need to have a net zero emissions, which means that we need to be able to remove the CO2 from the atmosphere rather than put it into the atmosphere. The mitigation patterns the mitigation here can be achieved through a number of different approaches, and one of which I'll be talking about today is the carbon capture utilization. Fossil fuels are always going to be an important consideration. We will not get away from fossil fuels completely, although we can reduce the use significantly as we get further and further electrification of our grid and things like that. This is the fossil fuels. This is the net negative amount of emissions we're going to need, and we can do that using negative emission technologies, and we'll be talking somewhat about that. The strategy for CO2 mitigation, clearly there's nuclear, there's solar, wind, and hydro, all of which are important and are developing even further nowadays. And then there's a whole area of carbon capture, utilization, and storage. So nuclear, solar, wind, hydro, of course, avoid the emission of CO2 at all, whereas the carbon capture, utilization, and storage actually try to do something with the CO2 that is being emitted nowadays, and we cannot avoid completely. And we can look at the capture, we can look at utilization, and we can look at storage capacities. In addition, this is to take into account what's happening in terms of emissions, but we can also look at how can we remove the CO2 from the air directly, and this is where bioenergy with carbon capture sequestration is of interest. There's direct air capture, taking CO2 directly out of the air, and then of course forestation, and these are all removal of the CO2 from the atmosphere. The Carbon Capture Center, our mission in the center is to conduct cutting-edge research. We want to look at techno-economic assessments, and we want to reduce the cost of carbon capture. We want to enable secure carbon storage options and develop carbon utilization opportunities. In my work today, I'm going to be talking a little bit more about the carbon capture side. That is where my areas of interest have been over the last few years. And in particular, of course, we have the power industry, we have the industrial industry, then we have carbon capture, carbon emissions from vehicle transportation. These typically are in the range of about 5 to 15% CO2 in the emissions. On the other hand, the other areas in which we could be of interest as well for CO2 abatement, some of which would not do much to solve our CO2 problems, such as in confined spaces, in submarines and aircraft and spacecraft and the like. Buildings, if we can keep the CO2 levels down inside a building, we can then avoid doing a lot of exchange of air outside to maintain low levels, and therefore reduce the air conditioning costs associated with this. And then there's also the whole area of looking at capturing CO2 directly from air at the moment. A number of companies are looking at that right now. And these typically we are in the order of about 0.05 to about 0.5% of CO2. So we can see that the scales over which we are looking at are enormous, and the concentration ranges are pretty significant as well. And what we need is a suite of different types of chemical technologies for mitigation of the CO2 releases. So if we look at the carbon capture, utilization, and storage space, the source of CO2 is power, is coal and gas, the power sector, the transport sectors, of course, and the industrial sector are all important sources of CO2. Whereas if we look at the storage side, we look at sequestration and geologic formations. We look at useful sequestration, such as enhanced oil recovery and mineralization. We're also looking at utilization, such as the development of chemicals and production of chemicals through either chemical or biological means to be used for fuels or chemical products or fine chemicals and the like. The important part, of course, connecting these two is that we need to be able to capture the CO2. And here we look at how can we go about doing this. Obviously, one of the ways we do it is to take a CO2-rich exhaust stream and pass it through an add or adsorber system in which we remove the CO2 and then we release a lean CO2 stream. This is good because we can now capture the CO2 directly. The problem is the adsorbent will tend to get loaded up, and we need to regenerate the adsorbent and release the pure CO2. So we take the CO2-rich adsorbent and take it to a desorber where we have some kind of energy input to be able to break the bonds or whatever it is that we have in the system and release the CO2 as a pure CO2 product that can then be sequestered or utilized in other ways. And then we can take the lean sorbent and take it back to the absorber and do this complete cycle. Now, there are a number of different ways we can do that, and I'm going to talk about a couple of new ways that we have been looking at that might be able to be exploited to do this efficiently. The capture of CO2, the release of CO2, the desorption can occur through temperature swings, in other words, raising the temperature, breaking chemical bonds. Pressure swings to release CO2 because of sucking it out, basically off the surface or out of the sorbent. And then we can also talk about electric potential swings, which is of some interest, significant interest to us. Now, if you look at the traditional amine process, to put things in context, the traditional amine process is the benchmark operation. We have an absorber system here. This is where the CO2 gets absorbed by an aqueous solution of amine, in this particular case, ethanol amine, and it interacts with CO2 to form a chemical, a carbamate. The chemical complex is shown here. This is generally done at about 40 to 60 degrees C, so fairly low temperatures. But to be able to release the CO2 and regenerate the amine, what we need to do is take this up to much higher temperatures where we can break the chemical bond and release the CO2 and regenerate the amine. This then is taken back from the desorber unit back through a heat exchanger where it's cooled down again and sent back to the absorber. So this whole process is rather energy intensive. It requires significant amounts of steam for the reboiler and the like, and generally it requires a certain amount of retrofitting and disruption of the steam cycle in a power plant if you want to install it in an existing power plant. So we were wondering, are there ways in which we can go about avoiding this huge energy requirement, the steam requirement, and do things under more isothermal conditions, but also with using electrical sources, which can be from renewable resources as well. So the basic idea we have here is very similar in terms of the absorption side. We have an absorption column in which we absorb CO2. We have the amines coming in. The CO2 is then captured by the amines to form the carbamate. But the difference is the way in which we regenerate these amines. Instead of sending this to a thermally heated up desorption column, we send this to an electrochemical cell, as shown here, where we've got these are copper electrodes. And what we do is when you oxidize the copper electrode, we release the cupric ions, and these will complex with the amines very strongly, displacing the CO2. So CO2 comes off now as a pure stream, and we can then release that to disengage that in the flash tank. Then this copper amine complex that we have can now be taken back to the cathode chamber of the electrochemical cell, where we plate out the copper, and in so doing, we regenerate the amines, and can then be sent back to the absorption column. So this is a pretty straightforward process now, and the thing is that the anode chamber really takes the place of the desorber, the thermal desorber, and the cathode chamber is more like the replaces the heat exchanger system that we have. This process works pretty well. This is a small bench scale system that we set up in our lab. You can see the desorber here. These are electrochemical cell with the copper electrodes separated by a membrane. The two chambers are separated by a membrane. Just to show you how this works, this is the applied current that we apply across that cell, and the higher the current, the greater the rate at which we release copper ions in solution, and therefore the greater the rate at which we will release CO2. And indeed, as we change the current passing through the system, we change the amount of CO2 that's being released directly, as shown here. Typically, we can get on the order of 80 to 90% Faraday efficiency for these systems. Obviously, what happens is sometimes the cathode, the anode will be corroded, and the cathode will grow with time. And at some point, we will need to flip chambers, change the polarity, and feed switch the feed to the different chambers. And this shows you the cyclic type operation is rather stable. This is on the order of 6 hours. We've actually run these on for more than 200 hours now, and we've got very, very stable operation of these systems. So the question is, what are the thermodynamics energetics of something like this? We can develop the thermodynamic program diagram as shown here. This is the potential versus the 1000 electrodes as a function of the amount of copper that's being released relative to the amine solution. And we start out here. This is coming from the bottom of the absorption column. at a pressure of about 0.13, a fugacity of 0.13 for the CO2. This is at a constant concentration here. As we start releasing copper into the system, we also begin to start releasing CO2, and we get at a constant pressure, and we get the CO2 loading goes, in this case, from 0.81 to 0.26 in the system. Then when you get to the end here, we take this up to the flash tank, and we then recirculate the CO2 lean copper-rich solution back to the cathode. We begin to reduce it. The concentration is constant the whole time, CO2 now, but as we reduce it, we're replacing out the copper, and we come back in this cycle. And total energetics are basically given by the area under this curve. So that gives us the minimum thermodynamic penalty. Of course, you have to worry about transport limitations and other kinds of kinetic overpotential required, etc. But once we've gone through and taken consideration of all these different kinds of things, such as deficit transport overpotentials and so on, we can develop an analysis of the work required to do this, the kilojoules, electrical equivalent of kilojoules per mole of CO2. And we find that we are very competitive with the other systems that are out there, advanced MEA, thermal EDA, advanced porosity. So this shows that basically the concept is a very viable concept in the system. And the economics are also favorable if you look at the cost of electricity. This is for the EMR system, the process we just been talking about, with the MEA and NDA and porosity thing. And we see that we are very, very comparable in terms of these. The overall capture cost depends on the shift in loading that we have in copper. How much of a capacity do we utilize of our system? And if you go between about 40 and 80%, you see that the loadings of the actual capture costs are pretty reasonable, depending on the price of the membrane, the cost of the membrane that we have in the system. But that seems very, very promising in this case. So just to summarize then, I've given you a very brief overview here. There's a lot more that's gone into it, in particular in terms of understanding the chemistry associated with these systems, electrochemistry, and the like. But the advantages of that process that we foresee that for this is it does not need steam and extensive retrofitting, which is a very strong advantage. It's really much of a plug-and-play type operation. It can be operated isothermally, which is also a significant advantage. We can desorb at pressure to some extent. And if we want to, we can also utilize low-grade heat to improve the efficiency, but it's not crucial. And it certainly has competitive costs and energy requirements. Now, what we do here is the agent that captures the CO2, the amines, are not really electrochemically active at all. What we do is we utilize the electrochemistry of copper to add to the amine solution to release the CO2. There are other ways in which we can do this and actually have the chemical reaction, the reagent itself, be electrochemically active, so we don't have to add a second component to the system. And one of these would be looking at Quinone type systems. There are a number of different systems we can look at. But this particular case, let's think about the Quinone systems in general, as shown here. Typically, these in the dormant state have no capacity for CO2. They're just pretty inactive. We can then, if we go through electrochemical reduction, add a couple of electrons to this guy. What you'll find is the electrons accumulate on the oxygens here. We've got various high electronic densities associated with this, which makes it a very active state for the capture of electrophiles such as CO2, which will form the dicarbonate as shown in this case. So this is a way in which we can then modulate, control the capture of the CO2 by controlling the electronic distribution on the molecules by reduction. And then when these are fully loaded, we can regenerate them by oxidizing these again, removing those electrons, oxidizing, going back to the dormant state, which has no particular affinity for CO2 whatsoever, and we can release the CO2 in a flash tank, and release the CO2, and then recycle these systems. The question is, how do we actually apply these in the case of one, in a real system? The idea we have here is to use an adsorption type process, not absorption, but adsorption, in which we'll have electrodes as shown here in a column, in a chamber like this. the CO2 will be flowing between the electrodes, and the electrodes would be functionalized with these quinone type molecules, where they would then capture the CO2 as they pass through this electrode stack and so on. So again, we've got the quinones coming in. This is that's a quinone coming in. It basically is reduced, capture the CO2, and then when you want to, we can release the CO2 by reoxidizing the system. The way in which we set this up is shown here, a sandwich type structure, where we have the CO2 in this particular one. We've got the pink ones here are the quinones in the reduced state, and they can then capture the CO2. We do need an electron source, of course, and we had that in the central electrode, which in this particular case is ferrocene. And when you have the ferrocene being oxidized to provide the electrons for the reduction of the quinones, we get the ferrocenium. So at some point, this electrode will now become fully loaded with CO2. We'll have no more capacity for CO2. In that case, we can just reverse the polarity, and the ferrocenes now get reduced. Ferrocenium get reduced back to ferrocene. The quinone, the dianion quinones get oxidized back to the quinone, and then release the CO2. So this is a typical swing type process that we'll have in this system. So let's just have a look at what we have to do here. One of the things, obviously, is that we want to have some degree of coupling between the redox coupling between the cathode and the anode sections. And we want to make sure there's some charge balancing in the system. So let's take a look at the electrochemistry here. If you look at the charge concentration on each of the electrodes, and then the bound CO2 concentration on the cathode, as a function of the potential relative to some reference potential. We know that according to the Nernst equation, we can relate the amount, the quantity of the charge amount to the actual applied potential relative to the steady potential here, and we'll get a curve that looks something like this. So this will tell us as we change the potential, they get more positive, the amount of charge on the system goes down, and the amount of CO2 that's bound also goes down. So you need to go to fairly negative charges here to be able to capture the CO2. On the other hand, we have the anode side, in which we have the ferrocenes get charged up, and they have the opposite behavior in terms of the overall structure of the curve. So this really gives indication then of the electrochemical advantages of the system. So if we apply a potential here, and we capture CO2, apply potential at this point, the amount of CO2 bound would be given by this quantity at this point. But because we need to have a charge balance, the electrons have to come somewhere to give us that charge concentration. We have the same charge concentration on the ferrocene electrodes as well. And this then gives us the capture velocity potential. When we actually capture voltage, the cell voltage, when you apply a voltage across the two electrodes, this is what you would need to get this level of charge transfer and CO2 binding to the electrodes. Then when you want to release, of course, we can apply a different voltage. And when you get the different voltage, we get, this would be the voltage that we would require to give us a bound concentration at about this level. So the total concentration swing, you might say, in terms of the CO2 that's captured and released is given by the difference between these 2 points over here. So how do we make these electrodes? Well, the easiest way to do them, not the easiest way, but one of the ways is to take the polyvinyl ferrocene as shown here, and we wrap these around carbon nanotubes in solution, and then do drop casting or dip coating or things like that to be able to generate the electrodes. This is the electrodes, the carbon fiber substrate for the electrodes. These are the actual polyvinyl ferrocene carbon nanotube films are shown here. This scale bar is 200 microns. If you zoom in a little bit closer, we've got 400 nanometer scale bar here. You can see it's a very porous structure. You can see all the carbon nanotubes here. These are coated with the ferrocene, so you get very large surface areas and a large porosity, which is good from a number of perspectives. The carbon nanotubes themselves ensure strong electronic conductivity. The high porosity facilitates ionic conductivity because we have these electrodes that are bound with an ionic liquid. And the large surface area makes them readily accessible to absorbents such as CO2 in this case. can do the same with the Quinone electrodes, a very similar kind of operation. We just do a polymerization of these anthraquinones and coat them in the same way and get very similar behavior. Now, the way some early tests we did was take the electrodes, and this is the electrode structure. This would be the Quinone electrode and a second Quinone electrode and a ferrocene electrode in the center. These are separated by a separator, sandwiched together like this. And then they are moistened with an ionic liquid as the electrolyte for the system. It also acts as a shuttle for the CO2, allows the CO2 to be absorbed and then transferred directly to the electrodes themselves. We then take this electrode, wind it up, and put it inside a sealed chamber, as shown here. We wind it up there. The electrical contacts, we can connect the two different electrodes, and the sealed chamber is then connected to a pressure transducer where we can measure any changes in pressure because of changes in CO2 concentration in the gas phase. We seal everything up, pressurize this with CO2 at any given concentration, and then flip the potential on and off to get an idea of how much CO2 is absorbed. As I say, we measure the pressure from the ideal gas law, can calculate the amount of CO2 absorbed, and therefore determine the effectiveness of this approach. This will show you what happens in this particular case. As we show here, let's just say in this case, we're going from the oxidized to the reduced state of the quinone, and we'll see that when the oxidized, you get little low concentration of CO2 on the electrodes, the amount absorbed, and when we go up to the reduced state, it gets absorbed pretty quickly and it goes back and forth. And you can see the cyclic efficiency is pretty good in a case like this. So we can go back and forth. We just fluctuated back and forth in terms of the oxidation reduction potentials. The overall capacity was pretty high. The normalized capacity over about 7,000 cycles. There was some reduction in capacity, which was because of, we understand why that is, and we know how to improve on that. But the important part is that we got about a greater than 90% Faradaic efficiency, and as I'll point out a little bit later, we got about 40 to 50 kilojoules per mole, which is a very respectable energetic penalty to pay for this overall capture and release cycle. We've also done this in packed bed type operations. This shows the normalized concentration in a packed bed. We have a packed bed like this. We have a CO2-rich feed, and we measure the outlet concentration. This is a normalized concentration outlet over inlet as a function of the number of bed volumes. Bed volumes is equal to the actual time of the experiment relative to the residence time within the bed. And what we'll notice is that initially the CO2 has been absorbed, so what's leaving the column here is very low CO2 concentration until such time as the bed is totally saturated with that particular concentration, and therefore the concentration of the effluent is rises to be up to the feed concentration. And as expected, you'll see for different concentrations of CO2 in the system, we will get different overall residence times required for saturation. And if we look at the normalized, everything falls up to one curve here. And this gives us an indication then of the total bed capacity and how effective it is these things are in terms of capturing CO2. These are some other examples. This particular case is a residual concentration coming through, which we think was just because of poor hydrodynamics in the system and inefficient packing of the electrodes. We have been able to do it where the actual concentration leaving the column, leaving the bed, is zero, essentially, for a large number of bed volumes before we get breakthrough in the system. So the energy utilization of a system like this is related to the charge transferred and, of course, the Faradaic efficiency, about 0.9. And then the difference between the capture and release voltages in the system. So if you look at this, we talked first about the capture and release voltages, as I talked about before. And this is the amount of CO2 released if we have this degree of these capture and release voltages. If we actually have a slightly more negative release voltage, what we'll have is this degree of, with this particular voltage, and the amount of CO2 released would be given by this. So remember the difference between the capture and release voltages. So we can see in this particular case, the capture and release voltages are significantly smaller. The difference is smaller than in this particular case. We use the yellow release voltage, but the amount of CO2 released is also less. But we can then evaluate from this the amount of the release, well, the energetics associated with the system. If we look at the amount of fraction released as a function of the release cell voltage, in other words, the capture and the difference between the capture and release, the capture voltage 1.3, the release cell voltage can change. We get delta V of 0.3, we get about a 55–60% fraction release, but you also get significantly lower energetics associated with the overall capture and release cycle. There's about 35 kilojoules per mole. So this is very, very encouraging, and all depends on how much of the capacity we want to utilize on the quinones as to what the energetics per CO2 would be. So this is very encouraging result as well. And indeed, if you look at the overall summary of these systems, what we've got, chemical swing, they are isothermal. There's no external heat sources. They are plug and play, can be really easily installed. They're readily scalable. They can be used at small scale and large scale type systems with ease. The favorable energetics, about a gigajoule electric per ton of CO2, and reasonable economics, we estimated with a 40 to 80 tons per CO2. This is actually for looking at direct air capture. The number seems really low for 80 tons per CO2, $8 per CO2, but we need to look into that a little bit more closely. And it's also available across multiple scales. So we actually have started up a company to look at this, a company called Verdox that started, not the best time to start a company in the middle of a pandemic, but it is getting up and going, looking at a number of different types of market opportunities. For the last 10 minutes or so, I'd like to talk to you about another system that we've been looking at and revisit the whole idea of what these different capture scenarios might be. We know there are temperature swing. We've talked about chemical solvents such as the amines for temperature swing type operations. There are pressure swing, which I've not talked about. These use physical absorption at high pressure into solvent, but then at low pressure to regenerate the solvent. And then we've talked about our two electrochemical potential swing systems here. We have others you can look at it as well. These are all operated low temperature, ambient temperature. The question is, are we able to operate at high temperature? Are the actual operations in which we might be more advantageous to operate at high temperature, at the temperature which the CO2 is actually produced, rather than having to cool the effluent gases down to low temperatures for use in these other systems? So why do we want to use high temperature intermediate temperature capture? If we look at take the fuel and oxidant, this would be the reactor. We take the hot exhaust, we get heat recovery from here, and we then take the cool exhaust, send to the absorber, and we get our CO2 lean, and we get a CO2 product from the desorber. On the other hand, if we switch these and did the absorption and desorption at the high temperatures at which they're produced, and then take the hot exhaust gas and hot CO2 go into heat recovery units, we can then get the same product eventually out at the other end. And the reason why this could be of interest to use high temperature recovery is that we get energy content of the fuel coming in here. We get useful energy to extract it from the heat recovery unit, and then some of that energy needs for regeneration, but that is then going to be wasted. It's going to be low-grade energy that's somewhat wasted at this particular point. On the other hand, if we look at the energy content coming in again, we do the energy for regeneration at the high temperature, and the recovered energy is of high quality, and it can then be go to the heat recovery unit, and we get useful energy coming out right at the end. Similarly, from the desorber, the useful energy from both the lean exhaust and the CO2 product can both be recovered rather effectively for the system. How do we go about actually exploiting something like this? But we need, well, we think we might have improved heat recovery, high efficiency, and lower cost is the holy grail here. The traditional solvents for CO2 capture are a very big value. And here, this is CO2 uptake in terms of millimoles per gram as a function of temperature. And these are traditional absorbents that people have been talking about. But we can see there's a very big trough, a very big valley in this region here. And this is the region in which we would be most interested in looking. So what we've been doing then is the high temperature or intermediate temperature carbon capture. For temperature swing, we have been looking at solid oxides. I won't talk about them now, but we have some significant impact, significant results on using solid oxides such as magnesium oxide and the like that show some very strong, powerful recyclability and capacities for these systems. We're also looking at metal oxides at the moment for electrochemical systems, but that is very, very preliminary work, and you don't have much to say on that at the moment. But what we're interested in, the high temperature systems. This is just showing that we are looking at magnesium oxide, which we've overcome some of the many limitations that people have had in the past by having molten alkali metal nitrate as a promoter for the CO2 capture and the formation of the magnesium carbonate in this particular case. We're not the only people, other people have also been looking at this. But the important part is that we are able to operate rather stably over many, many cycles as shown here. And what we've done is by having the promoter here, we can actually bring the CO2, we can overcome many of the kinetic limitations associated with CO2 capture and bring it up to looking at the equilibrium curve associated with this. We'll be limited by equilibrium rather than kinetics in the system. But what we're interested in again now is other systems that we might be able to use. These are solid oxides that we've talked about in the past, but we also recognize that we can reuse molten oxide systems that can have some significant advantages in terms of being able to well, we'll show you some of the advantages in a while. There are two different types of molten oxide we've been looking at. One is a liquid to solid, in which CO2, when it gets captured, it forms solid products. The other liquid to liquid, CO2, when it gets captured, it stays as dissolved in the liquid as molten oxides. These molten sorbents have good advantages in terms of reactivity with rapid kinetic stability and are able to remove contaminants simultaneously and be able to separate them, such as SOx and NOx. They can operate under isothermal conditions or pressure swings, and isothermal conditions with isothermal pressure swings, and they can also be highly efficient in use of reaction absorption enhanced designs. Just to show you quickly some results of these, this is a liquid to solid type system. This is the loading as a function of time when we challenge these sorbents with that, and you'll see that depending on the concentration, whatever happens, there's always this little knee that's coming in here. We get a fairly quick absorption rate and then a bit of a knee. And at this particular point, the sorbent is becoming saturated with the CO2, but you're also getting nucleation and formation of particles as shown here. And once that occurs, that keeps on driving up the CO2 up to a full loading of an order of 6 millimoles per gram, which is pretty respectable loading. If we're looking at the liquid to liquid systems, we do not see that need. We get much more stable, much more attractive kinetic results as shown here. But it does indicate that we are able to get really good loading at fairly low rates of absorption in these systems. So the stability, let me show you the stability for these two systems that they cycled over many, many cycles, these 100-cycle tests. And you can see that there's definitely no loss in overall capacity over this time. They're very stable in these operations. We're able to regenerate these isothermally using steam. So we have an inlet concentration CO2 coming in. This is when we capture it. And we have a sweet gas coming out, steam in this particular case, to release the CO2 into a steam stream. This is all done isothermally. And we can see that we get very rapid capture and release of the CO2 from these systems. And it is the purity of the release, CO2 is 100%. The capture is pretty about 90% capture in these cases. And you've got many, many cycles of stable operation. So if you just want to revisit this system here, what we've got is, again, our little valley of death, you might say, in terms of the existing sorbent systems. But we have been able to fill in this gap quite successfully, looking at our magnesium oxide systems, lithium borate. These are solid systems, and two different types of liquid systems, either sodium or lithium sodium borates that can operate in these particular temperature ranges. So we've been quite happy with the results to date. The question is, how effective are these going to be in terms of actual application? This is just one analysis we've done, looking at utilize these in the coal-fired power plant an analysis. What we have is a typical coal-fired power plant with the SCR and the FGD here, and all the other things that go on. And what we look at is some of the combustion is, this is the steam cycle. But if we can integrate these absorption systems in with in the boiler and the like, we can do a fair amount of work in terms of looking at the sulfur recovery, CO2 capture, release, and so on. So this is with capture. And the question is this going to be a viable approach economically? So let's take a look. We've done a fairly detailed Aspen analysis, design analysis of the systems. This is the rate efficiency of the power plant. This is the emissions in kilograms CO2 per megawatt hour. If we have no capture, the emissions are pretty high. Efficiency is about 46%. If we have a capture, the net rate efficiency is going to be about 33%, and we get about 80–90% capture. And emissions are greatly reduced. If we use our molten salt systems, according to our analysis, we get this range over here. The various cases we looked at, where the emissions level are similar to what we have for the amines, but the efficiency of the overall plant would be larger, would be significantly better. And if you look at this as being the base case here, we can then use that and do an analysis around that base case. And the question is, how does this compare in terms of costs? This is the cost of CO2 avoided using traditional amine on the order of about $50–$55 per ton, and efficiency again of about 34 in this particular case, 34%. Our base case, as we pointed out before, was close to 40% efficiency, and this is the costs are somewhat higher in terms of the CO2 avoided in this case. So by doing an analysis of a number of different combinations, whatever, we end up with this type of curve that's shown here, and relative to the base case. And the important part is that we have now been able to minimize the cost at some loss in overall efficiency, but not a really huge loss in overall efficiency. And it looks like this could be a very viable approach for us to adopt. Take the economic analysis. The levelized cost of electricity shows with amines, goes up by about 64%. With the molten solvents, we think it could be up to about 40%, significantly lower. And the cost of CO2 avoided would be shown here, $55 per ton relative to $34 per ton, around about a 38% decrease in cost of CO2 avoided. Of course, there's a lot of work still to be done in this case, the materials of construction, stability, and things like that. But this rather extensive, exhaustive analysis here indicates there could be some strong advantages associated with using these molten salt absorbents. So putting it all together, the advantage of the molten sorbents is rapid kinetics at high capacities. They're inherently stable and regenerable. They can co-capture other gases if needed. Can be regenerated by pressure swing or also temperature swing, depending on how we want to go about doing it. And the high temperatures can lead to improved heat recovery in these systems. So to summarize, we've looked at a range of different options here for new technologies for CO2 capture. Primary area has been in radioactive species, chemically mediated systems, in which we looked at a number of different approaches. I just described two today that look promising for overall CO2 capture. We also have solid oxide, which I've not really talked about. And then what we have introduced very recently are these molten salts as absorbent. Last part about the molten salts is that we can then consider combining the advantages of continuous type processing. So we can have the absorbent going from the sorbent to the desorber in a continuous way. So we do not have to worry about the normal switching and the cyclic swings that one needs with solid phase absorbent systems. So with that, I'd like to thank you, and I certainly would like to acknowledge the students and postdocs that have done the work over the last 5 to 10 years or so. Mike Stern developed the EMAR process. They've been really greatly improved by the others shown here. And Sahai Bastian was very much involved with the electrochemical system. And I do not have Cameron Halliday here. Cameron Halliday and Takuya Harada, I forgot to put them on, are two that work very extensively on the molten salts and have brought us to the point where I think it's actually a very viable approach. So with that, I'd like to thank you for your attention. I'd be happy to try and answer any questions you might have. Thank you.
Thank you, Alan. There are a couple of questions that have come in, which we'll get to. And maybe we should start with those, and they're rather specific, but we can move maybe to more general questions. I don't know if you can see them, Alan. If not, I'm happy to read them.
I'm trying to get my stop share here. There we are. This is the question.
The first relates to NOx and SOx impact on quinone absorbance.
Okay, that's a very good question. NOx and SOx. We haven't done much work with NOx, but we have done a fair amount of work with SOx. Obviously, the SOx are going to bind quite strongly to the quinones, and if you've got a low concentration of SOx, they can be absorbed, and we can tolerate that for a while until enough of the quinone has been poisoned. We lose significant capacity for CO2. At that point, we can just take it to a much higher oxidation state and release the SOx in a separate, take it offline and release the SOx. Alternatively, this is something we have shown, although we haven't published this yet, we can actually alter the quinones themselves to make them much less basic. And so they will absorb the SOx quite effectively without actually taking up the CO2. So I think that's a really important consideration in this case. And so, yes, we are able to accommodate these as well.
The same questioner asks the same question about molten salts.
The molten salts, yes. Again, what we find is with the SOx, I'm not sure what happens with the NOx. Well, there are two different things that happen there. SOx, what we find is that they tend to precipitate out. So the liquid molten salt, lithium sodium borate, with the CO2 as a liquid phase, but the SOx will tend to precipitate out. So one can, in principle, then take that off and have a purge stream to capture, to regenerate the SOx side. And that can be accommodated. The NOx, we have a different situation, and the NOx actually end up going in there, and we end up getting volatilization. And we can lose some of the sorbent. So that could be a bit of a problem that we need to address still.
Does that, the potential for taking up SOx and NOx in the same reactor mean that if a plant didn't have SOx and NOx abatement equipment attached to it already, as it might not in many developing countries, that this becomes a way to provide both, and therefore to lower the cost of scrubbing all the gases, including CO2?
Yes. What we have is in the power plant one I showed you, although the other thing as well. Power plant, we did have that built into that the schematic I showed you, in which we would have the SOx being removed as well directly along with the CO2 and generated and regenerated separately in the side stream. I should point out that the SOx problem is actually quite an important issue, for the quinones and things like that, in the maritime industries, where there's the new regulations in terms of SOx emissions. And I think that our system could be quite effective there for minimizing the overall costs associated with the systems. Yeah.
Joel Powell asks about integration with gas-fired versus coal-fired plants.
Yeah, there basically we're talking about the different concentration levels of CO2. I should see no reason why they should not be just as effective. We are busy doing some work now. I know that Cameron is doing some analysis of gas-fired systems. He also did analysis of cement industry and so on. So we should have those numbers in the next month or two. Particularly now, you can't spend any time in the lab. You've got all the time in the world to spend doing economic analysis.
It's a great time to be a TEA guy.
Yeah.
Have you been able to move toward real life demonstration projects with these devices? I know that you've got Verdox going. Seem to me the most.
Well, Verdox is certainly moving towards doing that. In fact, that is their goal. And hopefully the next year or two, we will have units out there. Small units initially, but not necessarily for looking at the large scale mitigation, but certainly for some direct air capture, and then utilizing CO2 there for various things like greenhouses and things like that. Very good demonstration units. But we will hopefully in the next few years be in a position where we can sort of do some very large scale type operations too. As far as the EMR process is concerned, we have been working with a company in terms of developing, assessing whether this would be something they'd want to put on board on one of their pilot plant facilities. The molten salts is really too new at this point. There's a lot of unknowns in terms of the materials compatibility and so on. I think we're overcoming some of those issues, but we need more experiments, which we are doing at the moment. We would be doing if we weren't at home.
Have you investigated the techno-economics of air capture with any of these techniques?
Yes. I can't say much about that, unfortunately.
Okay.
That was done during the fundraising stage for the investment stage. It was done in a separate study, but it does look very, very promising. I must admit, I find the numbers a little low. I'm a little surprised at how low the numbers are relative to what other technologies are, but have every faith in the people that did it. So maybe we're okay.
Low in the sense that the costs are low, or low in the efficacy?
The overall cost per ton of CO2 captured.
Okay, interesting. Joe also asks about the stability of the Quinone system.
Another good question. Clearly, the Quinone systems can, depending on the oxygen content and things like that, there are some issues associated with the oxygen reduction. But we feel that we can obviate these problems by modulating or changing the structure of the quinone so that the oxidation or reduction potentials are significantly more positive, and we can avoid some of the oxygen reduction systems, oxygen reduction problems. Yeah.
I think we've gotten to all the questions. Well, there was one other one about whether you properly accounted for the power consumption in the EMR process with the energy spent on the electromigration of ions between the electrodes.
Oh yeah, no, that's all been taken into consideration. That really is what's been built into that. Yes.
Yeah. I think that's it for the questions that have come in. Keep them coming if you have more. I just perhaps one more.
I just see there's one here. How does moisture interact with these absorbents?
Oh yes, right.
Yeah. With the quinone type systems, because it's very low moisture content in the electrolyte we have, the ionic liquid electrolyte has very low water content, and so we do not have much of an impact of water on the quinones at all. We don't see any impact there. We've actually also worked with quinone type systems in the water and salt kind of electrode system. So rather than using ionic liquid, we've used water and salt, very strong lithium salt, and shown just to be as effective using the quinones for CO2 capture. Mm-hmm. With the molten salts, we don't see any effect of water whatsoever at this point. Of course, there may be some other things we haven't seen yet, but we'll have to wait and look and get more experiments done. Now, we did that regeneration, steam regeneration of the molten salts, and we saw the cyclic stability. It was pretty remarkable.
I guess finally, a question relative to your center. I understand that you've initiated a seed fund call that sounded to me rather unique. I wondered if you might tell us a little bit about where you're heading.
Sure. What we had initially is the seed fund, we gave small grants to some of our, particularly our junior faculty members, to get them into the interested in the whole area, to try and bring them into the with the center. This has been fine, but we kind of felt it would be worthwhile now that the center members would get a lot more out of it if we had some large projects that we're running instead. So we had a seed fund call. We had 15 proposals or white papers come in. And of those, we selected 3 for full proposals. And by the end of May, we will have been down to figure out who we're going to give the awards to. We got some very exciting proposals, I must admit.
Oh, and is that all entirely funded from the seed contributions that members have already made, or did raise more?
Yeah, those will be from the seed fund, yes.
Oh, that's exciting. Great. Yeah. I guess with that, well, there's one more question that's come in, and it's absolutely timely. Will the slides be posted and available to members? Our usual answer.
Okay, guys, we're not members, so I don't think we're getting the slides. But anyway, that's extremely fascinating. You know, it seems to me, after being kind of an old guy that has seen things come and go, that there may be a breakthrough out there that will change the dynamics of the energy industry. You know, if a guy like this or other people doing this research can actually solve this emissions issue, I mean, we're pretty good on everything but CO2. And if the CO2 capture can be perfected at a reasonable cost, then all of a sudden that puts all these fossil assets back on the table again. Because what's the downside of really digging coal in West Virginia if the West Virginians want to, and they can sell it and make a profit, and it doesn't have any environmental impact other than digging a hole in the ground. So, I mean, I think, you know, with all of the issues, and I know you guys are either have finished your presentations or you're working on them, if you really start to look at some of those numbers, I mean, Kingston is one power plant that was roughly 2,000 megawatts when it was built, and it's probably derated to 1,500 now. But I mean, think about it. I mean, how many square miles of land are we going to have to sacrifice to take that to photovoltaics? I mean, is that really going to happen? And then there's all sorts of potential instabilities associated with that. I mean, it's cloudy. Well, you're going to put in, you know, 3 times as much capacity to make sure that you have a firm, you know, particular amount of power generation. I mean, there's a limit to that. You know, we don't have wind power potential in Tennessee. Now, Texas and, you know, out the plain states, they potentially do. People on the coast do. And so, but I mean, to think that we're just going to run out and go all renewables in terms of solar and wind, I'm just not, I don't think I'll see that in my lifetime. Now, you people may in yours, I don't know. But, you know, it's funny how the right development, the right discovery, the right system gets put together, and all of a sudden things change. You know, it used to be we had all this pollution coming out of tailpipes on cars. You know, the brown LA haze they talk about was NOx, and then catalytic converters came along. Well, maybe there's another converter that's going to come along that sticks on the end of your tailpipe that's going to capture CO2. And, you know, twice a year you'll take it and, you know, have the element changed out, and it takes, you know, I don't know. But, you know, there's all sorts of possibilities, and to try to predict the future on all this, I think is very difficult. So with that, I will hush up. I will send you links to this so that you might, if you want to watch it or forward it to somebody else. I mean, this gives you an idea of some of the research that's going on and some of the potential that's out there. So with that, I'm going to conclude the semester. Like I said, I'll be emailing out a take-home final to you either today or tomorrow. It'll be due roughly a week. It's just one problem. And then we will have in class, well, I mean, an I-Learn test at the exam period. It won't necessarily be in class. And it will cover the SOX chapter, the carbon capture chapter, and combustion questions, and maybe a few questions over these videos. But I'm not going to ask you detailed questions over all of the chemistry and details that this gentleman presented today. I wouldn't even entertain doing that to you. So with that, I will conclude, and best wishes to all of you. And if I can help you in the future, don't hesitate to reach out. Sir.